So what we were going to be talking about today is beginning our multiple lecture series on transient analysis of first order circuits. So the first thing that I'd like to do is talk about what a transient condition is. So let's say that we have the following circuit, where we have some current source IS in parallel with some source resistance RS. And then we have a switch. And our switch is going to be closed and it will open at time t is equal to 0. Sorry, I had to sneeze. And connected to that network containing a practical voltage source, current source, will be a resistor R and an inductor L, like so. And let's call this voltage V of t, this current IR of t, and this current IL of t. So if we were to plot our inductor current IL of t as a function of time, it should look something like this. So here's IL. Here are negative values of time. Here are positive values of time. So before our switch changes from closed to open, this is a DC circuit, okay? So we're going to assume that the switch has been closed for a very, very long time. And so we would have a simple DC circuit, and it should be fairly straightforward to see that the current flowing through the inductor, whenever this is a DC circuit with the switch closed, should just be exactly whatever IS is, okay? So at DC steady state, this is this time over here to the left of t is equal to 0. We're going to call this DC steady state. We should see that our inductor current has a constant value of IS. Well, the time after the switch opens is what's called our transient condition. So for time greater than t is equal to 0 plus, which is all time immediately after our switch changes position, our circuit is in an intermediate condition. And so let me explain what I mean by that, okay? So can we agree that there will be some inductor current before the switch opens? Does anybody not understand why our inductor will be carrying a current? Bradley. Okay, so at t is equal to 0 minus, our circuit would look something like this. We have our inductor, excuse me, our source IS connected to our resistor RS, connected in parallel to our resistor R. So our switch is closed at t is equal to 0 minus. What does an inductor look like to a DC circuit? A short circuit. So I'm going to replace my inductor with a short circuit. This is my inductor current IL at 0 minus. Just for the sake of argument, here's my resistor current IR at 0 minus. Here's my voltage V at 0 minus as well. So, Bradley, if the two resistors RS and R are shorted out, all of the current IS will flow through the short circuit that is representing the inductor in this DC circuit, which means that IL at 0 minus and all time prior to 0 minus would be exactly IS. Okay, everybody okay with that? So at t is equal to 0 minus and before, our switch is closed. We have a DC circuit and our inductor has some current flowing through it, which means it has some amount of stored energy, right? When our switch opens up, so for time, let's say for t greater than or equal to 0 plus, what our circuit looks like is this. We have IS. We have RS. When our switch opens up, we're going to treat it like an open circuit. So over here, we're going to have resistor R. Over here, we are going to have inductor L. This is our voltage V of t. This is our current IL of t. This is our current IR of t, okay? So since the circuit has changed in some way, we should observe a transient condition, okay? Transient condition literally just means seeing what's going on while our circuit is in a state of transition. So if our inductor current was non-zero at t is equal to 0 minus, what does the inductor current have to be at the instant in time t is equal to 0 plus, the instant after the switch changes states? Pardon? It has to be the exact same value because we know that the inductor current cannot change abruptly, right? So what that means is that the inductor had some amount of stored energy, and it still has that exact same amount of stored energy at that instant in time, t is equal to 0 plus. What's going to happen as time progresses is that the inductor current will continue to flow, but it will now be forced to flow through that resistor R, which is going to slowly convert that stored electrical energy into heat. And as that energy transfer occurs, we should see that the amount of current flowing through the inductor slowly trickles to 0, because eventually all of the energy that was stored in the inductor will be transformed to heat by the resistance, okay? So at a very, very, very long time, let's call this t is equal to infinity, we should observe that our current through our inductor goes back down to 0. Everything to the right of t is equal to infinity is back at DC steady state. So what our goal is today is to figure out how this circuit behaves between t is equal to 0 plus the moment the switch changed positions and t is equal to infinity, where all of our energy has been transferred. Okay? So that's what transient analysis, excuse me, is all about. All right? So let's look at this circuit for t is greater than or equal to 0 plus, because that is literally the definition of our transient condition. And let's do some calculus, actually, okay? So if I apply Kirchhoff's current law at this node right here, I'm going to call it, just for the sake of argument, node A. I get IR of t, the current flowing through my resistor, plus IL of t, the current flowing through my inductor, sum together to 0. Kirchhoff's current law is the law of conservation of charge, so hopefully that makes sense, right? So IR plus IL should be equal to 0 based on the directions that I've given you guys, okay? Now, at this point in our circuit analysis careers, as it were, we know how to express both of those currents in terms of the common voltage V of t, right? So for instance, we can use Ohm's law to express the resistor current IR of t as 1 over R times V of t. And we can use the relationships that we developed, I believe it was last Wednesday, maybe, to express the inductor current as, let's see, sorry, I'm having, oh, excuse me, the inductor current with related to the voltage would be 1 over L times the integral of, and let's call it from negative infinity to t of v of x dx, and set this equal to 0. Okay. What I'm going to do now, because I've made a slight mistake in my derivation here, and so I'm going to attempt to fix it to make our life a little bit easier, I'm going to take the derivative of both sides of this equation. Okay. So if I take the derivative of the left-hand side with respect to time, what I will find is that I get 1 over R dv by dt plus 1 over L times V is equal to the derivative of 0. Everybody okay with that? So I just took the derivative of both sides of my relationship. And what I have now is a first order differential equation. And it's a homogeneous differential equation because it's set equal to 0. So what I'm trying to find here is some mathematical function that satisfies this differential equation. Okay. So can anybody think of an equation where the equation itself and the derivative have effectively the same form? Pardon? The exponential function, right. So we could assume or make a guess that our voltage here, V of t, will be of the four, what the heck just happened there? A e to the st volts. Okay. So it's an exponential that has some characteristic S that tells us how that exponential either grows or decays. And additionally, it has some magnitude A that tells us, how big it is at t is equal to 0 before it begins to either grow or decay, right? So it's an exponential function characterized by some magnitude and some rate of decay, S. So if we put this guess value into our relationship, what we will get here would be 1 over R times the derivative of the voltage. So what's the derivative of the voltage going to be? What's the derivative of A e to the st? A s e to the st plus 1 over L A e to the st is equal to 0. I'm going to give you guys a moment to copy this down, and then I'm going to go to the next page on my little tablet here. So what I'm about to do is just group like terms. Actually, I'll write it down here and I'll copy it over so I don't want to make another mistake in the algebra here. So let's call this, we're taking out a factor of A. Oh my gosh, what the hell keeps going on? Taking out a factor of A. About to get frustrated. Then we're going to have one over L plus S over R multiplied by e to the st is equal to 0. So I'm going to copy that, and that's where we're going to start with on the next page. All right. So if A is equal to 0, what does that mean? Everything is 0, right? So effectively, A is what's called a trivial solution to this differential equation, and it represents a state in which we never charged the inductor to begin with, or the inductor never had any stored energy to start with, okay? So while that's true, that's definitely not the situation that we had, because we observed that the inductor current was non-zero, which means there was some energy stored. E to the st can get close to 0 for particular values of S, but generally speaking, e to the st isn't 0 either. So really, the behavior of this circuit is defined by this bit right here in the middle, which is called the characteristic equation. So we could say that 1 over L plus S divided by R has to be the bit that goes to 0, because that's the only thing that will satisfy this in a general sense, okay? So what value of S, our rate of decay here, satisfies this relationship? Negative R over L. So for S is equal to negative R over L, our relationship is satisfied, so we can update our guess slightly. So that was that V of t in this case was A e to the negative R over L t. okay? And so now we need to figure out how to determine that coefficient A. Well, coefficient A, like if we evaluate, let's say, V at t is equal to 0, we would have A e to the negative r over L times 0. What's e to the negative r over L times 0? Exactly 1, which means our coefficient A is just the initial condition on our system. Okay, so it happens to be whatever the voltage V was at t is equal to 0. Specifically, t is equal to 0 plus, and I'm saying that because we need to be looking at this during the transient condition, because that's where all of this derivation occurs. And the transient condition does not start until t is equal to 0 plus after our switch has changed state. So we know now that our voltage V of t is of this form. V at 0 plus e to the negative r over L of t for t greater than or equal to 0 plus. So all first order RL circuits will behave this way because we solved it generically, all right? So I want to look at our circuit for t is equal to 0 or greater than or equal to 0 plus again. I'm just going to redraw it here. We had some inductance. I think I drew the resistor on the left. We had some resistance R. Here we have some inductance L. Here is our voltage V of t. Here is our current IR of t. And here is our current IL of t. Okay, so we did a big derivation here using calculus and all kinds of gobbledygook. And we found that our voltage in this case, which is representing the voltage drop across the resistor, as well as the voltage drop across our inductor, has this form where it's whatever value it had at t is equal to 0 plus multiplied by some exponential decay function, right? So what shape should the currents have? What should IR of t be now that we know how V of t behaves? Right. Ohm's law tells us that V of t over R is just the resistor current, right? Is there any reason it shouldn't continue to be that? Absolutely not. So this would be V of 0 plus divided by R, e to the minus R over L multiplied by time. Or another way that we could look at this would be IR at 0 plus e to the negative R over L times time. So if our resistor voltage has the form, this exponential decay form, it stands to reason that our resistor current has the same form, right? Just divided by R. So effectively, if we have an exponentially decaying voltage over resistor, we should see an exponentially decaying current flowing through the resistor. Anybody have a problem with that? That's what Ohm's law tells us. What about the inductor current? What was that, Connor? So we could do the integral of the voltage, absolutely, but let's be lazy. Negative IR, right? Kirchhoff's current law tells us that this has to be true. So that would just be negative IR 0 plus e to the negative r over LT, which we could just as easily write as IL at 0 plus e to the minus r over LT. All of our signals, all of our voltages, and all of our currents in one of these transient analysis problems will have this form, because Kirchhoff's voltage law and Kirchhoff's current law forces that to happen. If one quantity behaves that way, like what we derived for the voltage, all of the other quantities have to have that exact same wave shape in order to satisfy KVL and KCL. So, circling way back around to that graph that I drew on the front page here, we can say that this is going to have some exponential decay like this. That is just IL at 0 plus e to the negative r over L t. Okay. And I hope I have proved, let me go back down to the bottom here, that generically, I could say that y of t, which may represent a current or a voltage in our first order system, will be of the form y at 0 minus for t less than 0 minus, so however it behaved during DC steady state. And then after our switch opens up, it will behave like y at 0 plus e to the negative r over L t, or t greater than or equal to 0 plus. We can check our work, prove that this is how this behaves. Okay. So the power absorbed by our resistor, I can express it as the inductor current as a function of time squared multiplied by the resistor value. Does anybody have any problem with this? I can get away with this because I'm squaring the quantity, right? So it really doesn't matter the direction of the current that's flowing through the resistor, but power is I squared times R, which is perfectly valid here. So this would be I at 0 plus squared multiplied by e to the negative 2r over L multiplied by time. So that's my I of L quantity squared. So I'm just squaring the magnitude and then multiplying the exponential portion by itself, which is where that extra factor of 2 came from. And then I multiply this by a factor of R. The energy absorbed by the resistor from t is equal to 0, t is equal to infinity, which is when our inductor starts transferring energy to the resistor. T is equal to infinity is when the inductor stops transferring energy to the resistor. So we just have the integral, the energy absorbed by the resistor is the integral of the power delivered to the resistor. Anybody got a problem with that? So if we substitute in our mathematical relationship here, we're going to have 0 to infinity of R, which is a constant value, times IL at 0 plus quantity squared, which is a constant value, times e to the negative 2r divided by L multiplied by time. If I take those constants out, I get R times IL at 0 plus squared times the integral from 0 to infinity of e to the negative r over, 2r over L t. Oh, and missing my dt here. I should put it here. So what's the integral of e to the negative 2r over L? How do I do that integration? Anybody remember how to take the the integral of an exponential function? Negative L over 2r. So I take the, as a quick aside here, because I think this is important. We talked about it the other day. The derivative of e to the alpha t was alpha e to the alpha t, and the integral of e to the alpha t dt was 1 over alpha e to the alpha t, right? So doing that integration, we get r over 2r, needed my negative sign, and L should be in the numerator. And then we have e to the negative 2r over L times t, evaluated at infinity and 0. Well, obviously these r's cancel each other out, leaving us with negative L over 2. Oh, and I'm sorry, I forgot my I. Let me tuck that in here. I L 0 plus quantity squared. So what's e to the negative infinity? 0, right? Because e to the negative infinity is the same as 1 over e to the infinity, or 1 over infinity. What's e to the 0 again? 1, so that's minus 1. So this becomes 1/2 L IL squared, which we know for sure to be the amount of energy stored by the inductor. So our guess value for how this guy behaves has to be true because we've satisfied law of conservation of charge, law of conservation of energy, all that kind of good stuff, okay? All right, so let's talk about analysis for these problems. We never have to do this calculus again, ever, okay? We know how these circuits behave, full stop, because we derived it for a generic situation where R could have any value and L could have literally any value. So now I want to walk you guys through the level of circuit analysis that I expect of you, okay, for a particular problem. So let's say that we have the following circuit. where we have a 1 millihenry inductor, a 1 kilo ohm resistor, a 1 kilo ohm resistor here, a switch. Let me draw this better. That opens at t is equal to 0. Another 1 kilo ohm resistor. Yet another 1 kilo ohm resistor. And finally, 1 milliamp current source. Okay. So this circuit is a little bit more complicated looking than our last circuit, but it will actually behave in the exact same way. We just have to, instead of seeing a single resistor, figure out the equivalent resistance that's connected to the inductor during the transient condition. But we'll get to that step in a little bit, okay? So I have a very formulaic approach to solving these problems, as I do to most problems. And I'm going to teach you the steps that I use to make sure that I get the answer correct effectively every time, okay? So our first step is going to be, oh, and I should define some quantities here. So I want to know what my inductor current IL of T is, and let's say sorry, that looks like an R, but it should be an L. My inductor voltage VL of T is here. The expectation might be that we're going to do some calculus. We are not, okay? So these are our two quantities of interest. Our first step will be to analyze the circuit. At T is equal to 0 minus. So this is effectively really us checking on how the inductor behaves at T is equal to 0 minus, because we know that it cannot change abruptly. So however it was behaving at 0 minus is very important to our understanding of how it behaves at T is equal to 0 plus, and then the rest of the transient condition, okay? So at T is equal to 0 minus, what should this look like? Let's start from left to right. What should our inductor look like at T is equal to 0 minus? A short circuit, because T is equal to 0 minus always represents a DC steady state condition. So we should be replacing our inductor with its DC steady state equivalent, which is a short circuit. So here is our inductor. Here is our inductor current, IL of 0 minus. Here is our inductor voltage, VL of 0 minus. Our resistors should all just be resistors, right? Nothing should change for them at all. What does our switch look like at T is equal to 0 minus? It's closed, so it's going to look like a short circuit. right, so is everybody okay about this schematic being used to represent our circuit at t is equal to 0 minus? Anybody got any questions, comments, or concerns? All right. So let me ask you guys, we're going to try to figure out what IL at 0 minus and VL at 0 minus are. Anybody care to venture a guess for either of those two quantities? 0. For which one? Both. Absolutely correct. Why is the inductor voltage 0? Right. So the inductor voltage at t is equal to 0 minus will always be 0 volts because we are representing the inductor with a short circuit. And the voltage drop across a short circuit is always 0 volts. So we know definitively VL at 0 minus must equal 0 volts. Don't have a choice in the matter. Okay. Carter, why do you say the current is also 0? Exactly right. So the short circuit in the middle here prevents any current from the source from ever reaching effectively the left-hand side of the circuit. Okay. So it should be fairly obvious. 1 milliamp of current is entering this node, and then it sees two paths, a 1 kilo ohm resistor and a 1 kilo ohm resistor, right? So half of it should flow this way. The other half of that 0.5, or excuse me, the other half of that 1 milliamp should flow this way. And then we know that we should have 1 milliamp of current here. So all of that half of a milliamp stays like so. So Kirchhoff's current law is forcing it, no current to go off to the left-hand side of the circuit. And so we can easily see that IL at 0 minus is equal to 0 amps. Right, but intuitively, I'm just saying none of the circuit, none of the current can flow is just as good. I just wanted to mathematically show it to everybody here, okay? So that's step one, analyze the circuit at t is equal to 0 minus. Anybody have any questions, comments, or concerns about our analysis at this particular point in time? Okay. Step two is going to be analyze the circuit at t is equal to 0 plus. Okay. So at t is equal to 0 plus, but here's where things might seem a little wonky, okay? At t is equal to 0 plus, we are only considering that one instant in time, all right? Immediately after the switch has opened up. So if the inductor current at t is equal to 0 minus is 0 amps, what does the inductor current at t is equal to 0 plus have to be? 0. I'm going to keep slowly saying it until it burns its way into your brain. Bradley.
Isn't that because it's just a single point of time at steady state? It's only transient like a variable key?
So the reason, okay, so let's unpack this real quick. Okay. So for all t less than 0 minus, that's before the switch has changed state. So that's all DC steady state. T is equal to 0 plus is the first instant in time during the transient condition, okay? Now, I am not trying to suggest that the current IL will be 0 for the duration of the transient condition. I am only saying that it will be 0 for that particular, actually, hold on, we have a little bit of a problem here. So the problem that we're going to have here is that if there was no current stored, then there can't be any energy transfer. Now, I'm going to fix this. Okay. So the circuit that we're actually working right now is still a first order transient analysis problem, but it's what's called a driven problem. And what I mean by that is it's starting with no source connected to the inductor, and then we are effectively adding a source in. And that's going to behave in a particular way that I absolutely intended to talk about on Friday. But today I'm trying to talk about what are called natural response problems where the sources are taken out. So to correct my mistake here, let's change the direction of the switch, okay, before we unpack a bag of worms that I'm not quite ready to talk about here. So let's say that the switch was open and then it closed at t is equal to 0. And I apologize for the confusion and having to go back and redo this analysis, but it's going to get confusing real fast if I don't. So my apologies. I can't even read my own schematic diagram. All right, so at t is equal to 0 minus, the voltage VL is still definitely going to be 0, but I would argue that our current is going to be non-zero now, which is important because we need some amount of energy being stored. Again, I apologize for my jackassery. So how do we determine that current, IL at 0 minus? We absolutely could do multiple applications of current division. And so what I mean by that is that we know some current, so we know that there's 1 milliamps flowing into this node, and that some amount of current is going to flow to the left through that 1 kilo ohm resistor. And then whatever that current is, let's just call it for the sake of argument, I sub x. I sub x is going to hit this node. Sorry, that should have still been in blue. I sub x is going to hit this node. And that's going to split. And some of that will be the IL that we're looking for. So we could do multiple applications of current division to get that result. Is that how you guys want to proceed, or do you want to try something else? I don't think it is. So the reason why I say it won't split in half again is so if we applied current division here, what's the total resistance seen by that current IX? It's not 1 kilo ohm. It's 1 kilo ohm in series with half a kilo ohm. So it's not going to be just simply a quarter of a milliamp. Does that make sense? Okay. So because it splits twice, we have to, when we do our first bit of current division here, we have to look at the total resistance seen. So that would be 1K in series with a half a kilo ohm. Find out that IX and then split that again. And it's going to be whatever 1/2 IX is. We could also do mesh analysis. We could do nodal analysis. We can do any circuit analysis technique that we feel comfortable with to determine this quantity. So this is completely open to what you guys want to do. Okay. So raise your hands if you want to do current division method. I see 2 people. Okay, raise your hands if you want to do mesh. See like 8 to 9 people. What about nodal? Like 2 people. All right, mesh it is. I'll do these in green. All right. So let's call this guy right here our current IA. This guy right here, our current IB. And this guy right here, our current IC. So we can see right off the bat that IC is equal to -1 milliamp. Everybody okay with that? All right. Now we would need to do Kirchhoff's voltage law loops around meshes A and meshes B, right? So that would look like 1 kilo ohm IA. Let me save this and reopen it because it's going to keep on doing this pop-up thing here that's going to drive me insane. All right. So we're going to have 1 kilo ohm times IA plus 1 kilo ohm times IA minus IB is equal to 0. So that's our KVL around mesh 1 equation, which I hope I got correct. Then we have our KVL around mesh B equation. So that's going to be 1 kilo ohm IB minus IA plus 1 kilo ohm IB plus 1 kilo ohm IB minus IC is equal to 0. And so we now have effectively 3 equations, 3 unknowns, and we can solve for those 3 quantities, IA, IB, and IC. Someone tell me what you get. Anybody get something? All right, anybody else get those results? Okay. So, pardon me. If we know that these are our mesh currents, what should IL be related to these mesh currents? Negative IA, exactly right. So IL at 0 minus is negative IA, which will be positive 0.2 milliamps. All right. With our switch opening the correct way, are you all satisfied with our analysis that we've done here at t is equal to 0 minus? All right. Now we can move on to t is equal to 0 plus, which is step 2. Okay, so at t is equal to 0 plus, as I was mentioning earlier, before I noticed that this was not going to work out right because I had my switch effectively in the wrong direction here. The current flowing through our inductor cannot change abruptly. So whatever value it had at t is equal to 0 minus, it must continue to have at exactly t is equal to 0 plus, okay? So it's obviously going to change as time progresses, but that very instant t is equal to 0 plus is what we're going to look at here specifically, okay? So at t is equal to 0 plus, our inductor current was 0.2 milliamps direction down. We need to force that to happen now. And so what I'm going to do to force that is I'm going to represent my inductor at this one very specific point in time by a current source that has the same value of IL at t is equal to 0 minus and the same direction as IL at t is equal to 0 minus, because this will force that current to be whatever it was, right? So I'm going to redraw my circuit with my inductor represented by a 0.2 milliamp source direction down, okay? Again, the reason why I do this is because I need the inductor current to be a constant value at this very specific instant in time. Then I have my 1 kilo ohm resistor up top, my 1 kilo ohm resistor up here. Now my switch is actually behaving like a short circuit because it was opened at t is equal to 0 minus. Let me double check that so I don't make another jackass mistake here. Yeah. Then I have this 1 kilo ohm, this 1 kilo ohm, this 1 milliamp. This is my inductor voltage, VL at 0 plus, which may have a different value than what it had previously. My best bet is that it absolutely will. And then this represents my inductor current, IL at 0 plus. And we know 100% for sure that IL at 0 plus has to be 0.2 milliamps because the current cannot change abruptly. Whatever value it had at t is equal to 0 minus, it must continue to have at t is equal to 0 plus. So the only other quantity that we are interested in here is that voltage. Anybody have any thoughts on calculating it? Carter. Okay, so all right, but I would say let's not necessarily do mesh A. So let me show you the loop that I'm going to use. I like where your head is at. I agree with it. The loop that I'm going to use is this one. The reason why is because if I arbitrarily chose to include this 1 kilo ohm resistor, I might facetiously believe that there is some current flowing through it and voltage drop over it, when we know that can't be true because it's in parallel with a short circuit, right? So the voltage drop over that 1 ohm or 1 kilo ohm resistor, at which I've drawn an arrow pointing to it, has to be 0 volts, okay? So with that in mind, what is, let's see, so our current is circulating in such a way that it's flowing like this. So what's the voltage drop over this 1 kilo ohm resistor? 1 kilo ohm times 0.2 milliamp should be 0.2 volts, right? If I do KVL around my orange loop, I should easily be able to see that VL at 0 plus is what? Negative 0.2 volts. Because we have, if we do KVL around that loop, we have a whole bunch of zeros, and then plus 0.2 volts plus VL is equal to 0, which means VL has to be negative 0.2 volts. Okay. Anybody have any questions regarding our circuit analysis here at T is equal to 0 plus? Okay. As Carter observed earlier, with that short circuit in the middle there, the 1 milliamp source on the right-hand side no longer influences the behavior of the inductor or this resistor or this resistor. So the question here is, what is the resistance seen by the inductor during the transient condition? Okay, we're going to do this formally right now, but you'll learn to effectively do it pretty quickly in your head and intuit what's going on. All right, so step 3 is to determine the equivalent resistance seen by the inductance. Okay. Once I introduce a concept called time constant, we're going to rename this step, but it's effectively doing the exact same thing. Okay. So we are trying to determine the Thevenin equivalent resistance with respect to our inductor. Okay. So what does that mean we do? We take the inductor completely out, and we have to turn off all of our independent sources. So if we take the inductor out, and we're going to look in through the terminals where the inductor used to be, we have our 1 kilo ohm resistor, our 1 kilo ohm resistor, our short circuit, because we're trying to find out what the inductor sees during the transient condition. So it has to be what the circuit looks like after the switches change states. And we're going to open circuit over here because we need to be looking at a dead network. 1 kilo. Okay. So what is the equivalent resistance that we see? 1 kilo. That's it. We only see this guy, all the others wind up getting shorted out. So step 4 here. Will be use the results of steps 1 through 3 and plug in values to our generic equation. So our generic equation was y of t was equal to y at 0 minus, or t less than 0 minus, and y at 0 plus e to the negative r over L t, or t greater than or equal to 0 plus. So that means for our inductor current, IL of t will look like 0.2 milliamps for t less than 0 minus, because that's the value it had at t is equal to 0 minus. And then it will look like 0.2 e to the negative r. So that's 1 kiloohm over 1 millihenry, r over L t, or t greater than or equal to 0 plus. And we can clean this guy up a little bit, right? That would be 0.2 e. So what's 1 kiloohm over 1 millihenry? Yes, that's a million, right? So negative 10 to the 6th t milliamps for t greater than or equal to 0 plus. What about our voltage, VL of t? We can do the exact same thing, right? So our voltage at t is equal to 0 minus was what? Look back a page or two. 0 volts. What was our voltage at t is equal to 0 plus? Negative 0.2. And it will also have the same exact exponential decay rate. So it'll be negative 10 to the 6 t volts for t greater than or equal to 0 plus. What we could do to check our answer here, if we felt so inclined, would be to take the derivative of the current, multiply it by the inductor value, and we would find that we should get VL of t either way, right? So what I mean by that is we can use our calculus-based relationship. So obviously, VL is L DIL by dt. We can use our calculus-based relationship to figure out what VL of t is. Or we can literally use our generic equation because we know how the inductor voltage has to behave anyway, right? And I would argue that using our generic equation and plugging stuff into it is probably a bit easier than doing calculus every time we want to know what one of those quantities is, okay? So this generic equation was stated previously will work for any first order RL circuit. So that means any circuit that contains a single equivalent inductance connected to a single equivalent resistance, effectively. Okay. Somebody singing? All right, so I have a bit of a conundrum here. Okay, so this is the conundrum. I would like to talk about capacitors and how they behave today as well, or first order RC circuits. But between the technical difficulties and some mistakes I've made giving this lecture by setting things up a little oddly and all that kind of stuff, we actually only have 24 minutes left of class. And I think it would be better served for you guys to work on the in-class assignment than for me to rush through something and potentially make more mistakes and confuse you regarding how capacitors behave. So I'll save the capacitor circuits until Friday, with the understanding that my lecture might be a little longer than usual, assuming we get started on time and all that kind of good stuff. Does that sound reasonable? All right. All right. Sorry for all the insanery today. Pardon? I'm going to say yes under the assumption that they fixed the projector. If it is not fixed, I'm going to try to get there early and figure out whether or not the projector works so that we don't wait 15 minutes or plus trying to find a new room and all that kind of crap if we have to. For any of you who have not yet taken your exam due to COVID quarantine and all that kind of stuff, please come talk to me like now.